Okay, so we have here a practice problem based off of Kepler's laws. Let's begin by reading the problem. It says a satellite orbits a large 4.178 times 10 to the 24 kilogram planet, and it takes 4.32 times 10 to the 6 seconds to complete its orbit. The radius of the planet is 5,000 kilometers, and we're given a number of tasks here. First, we have to determine the total radius, calculate the altitude of the satellite, and then finally calculate orbital speed of the satellite. So let's start first by identifying known quantities. Right, the first value they give us is 4.178 times 10 to the 24, and that happens to be the mass of our planet. And let's go ahead and write that down. Okay, times 10 to the 24 kg. Alright, no need to convert there, it's already in the standard units. And let's see, what's our next quantity here? 4.32 times 10 to the 6 seconds, right, to complete its orbit. So that's going to be our orbital period, which is represented by capital T. Okay, and I can write that down, 4.32 times 10 to the 6 seconds. And lastly, we get the radius of the planet, about 5,000 kilometers up here. And this is not standard units, so we have to convert that. And when we do, there's two ways to go about converting this. You can either just multiply by 1,000, or just move the decimal to the right 3 times. Now you have your radius of the planet in standard units. So, R1 is going to be considered our first radius, or the radius of the planet. It's going to be about 5 million meters. So now we need the total radius, which is essentially, for us, it's going to be regular r. And that's our first task. Sticking to Kepler's law, or third law, he said the period is equal to 2 pi times the square root of r cubed times, r cubed over the gravitational constant times mass. And we know enough of these quantities to solve for r. We know the period, and we know the mass of the planet, and gravitational constant is just 6.673 times 10 to the negative 11. And let me just write it up here just to make sure. G equals 6.673 times 10 to the negative 11. And the units for this is Newton meter squared per kilogram squared. Okay? Now, since we know all these quantities, let's go ahead and just plug them all into Kepler's orbital period formula. So what is it going to look like here? I'm going to write this part in orange. It's going to look something like this. It's going to be 4.32 times 10 to the 6th power equals 2 pi times the square root. It's going to be square root of r cubed. R cubed, or I'm sorry, r is a quantity that we don't know. That's going to be the total radius. And we know g, which is 6.673 times 10 to the negative 11, and then multiplied by the mass of the planet, which is 4.178 times 10 to the 24. I apologize, I did kind of run out of room there. Right, looking at this, we can probably just solve the, let's solve the bottom first, gravitational constant times the mass, just to make that look a little bit nicer. Right now it's really cramping our formula here, but let's solve that, and if we multiply those two numbers together, I'm going to start from the right here, well, equals 2 pi, okay, r cubed And if we multiply the two bottom numbers here, we are going to get, around to the second decimal place here, 2.78 times 10 to the 14. Okay. And on the left side of the equal sign, we still have this value right here, 4.32 times 10 to the 6. Alright, and just to be clear, I kept the units out just for the sake of space. But keeping units in is actually a good habit. Okay. So right now, what I'm going to choose to do, what I think is a good idea to do next, is to take 2 pi and divide it on both sides. Now remember, if you are obviously doing this in your calculator, divide the 2 pi in parentheses here. Okay. And this scientific notation number needs to be in parentheses as well. Okay. And when we do that, we're going to get 4.72 times 10 to the 11 equals r cubed over 2.78 times 10 to the 14. Okay. And so what's our next step here at the very end? Alright, so to solve for r, we're going to have to multiply the 2.78 times 10 to the 14 to both sides. Okay, let me just erase some room here on the left. We're going to have to clear this. I hope you have this written down already. We have to clear this. And let's continue with our problem. We're going to multiply both sides by the denominator number here, 2.78 times 10 to the 14 to both sides. And when we do that, we are going to get 1.314 times 10 to the 26 equals r cubed. And the last step here to solve for total radius, we have to, since total radius is, or r is raised to the third power, to get rid of the third power, similar to how you get rid of the second power, you would square root it, but with the third power, you would cube root both sides. Okay. What does that look like potentially in your calculator? Well, you have two options here. If you can find the button in your calculator, it's typically followed by a second function. You would do 3 root, and typically you would have to fill this 3 in yourself. Okay. And then you would follow by putting this number in there. Okay. But if you are unsure where that button is and you don't have that, well, what we can do is we can take this number right here. Let me write it down right here. 3.14 times 10 to the 26, and put this number in parentheses and raise it to the 1/3 power, like so. And it's probably good to, when you use a caret symbol in your calculator, you can probably, it's good to put this in parentheses as well. And you do it to both sides, of course, and the r will go away. I'm sorry, not the r, the cubed will go away. We won't need that anymore. And when we do that, I solved the radius, the total radius, to be this value right here. Huge quantity, which is completely acceptable because these values are happening in space, and this is equal to r. Okay, and just to be sure, this value is our answer right here, guys. Alright. Okay, that's the first part. For the second part, I'm going to go now erase this entire screen here. We need to kind of more or less start over. Not start over, but make some room for ourselves. I'm going to erase this screen. And now we need to find the altitude. Now remember, because the satellite's orbiting this planet, there's really two distances to consider, and we more or less call it R1 and R2. R we call it the total radius, and then there's R1, which was the radius of the planet, and R2 is the satellite altitude. Because if you add the radius of the planet and the altitude of the satellite, that's actually how far the satellite is from the actual center of the planet that it is actually orbiting, right? But we just saw far, all right, this was that huge number we had earlier, 508, 414, 019.4. All right, this is in meters, remember that? And what was that? That's 508,414,019.4 meters. This step is actually quite easy because we just we were already given the radius of the planet. We said that was, we already converted that a while ago. That we would consider R1. That is 5 million. And actually, if you take the difference of these two, or if you actually plug the values in, this looks like a very similar algebra problem. If I just plug everything in like so, equals R1 5 million plus R2, and you look at this, and this looks very, this is basically an algebra problem, and all we have to do here is subtract both sides by 5 million to solve for R2, which is what we're using to represent the altitude of the planet. Okay, and when we do this, this side crosses out, and this side, when we solve for R2, we're going to find that the altitude of the satellite is not, well, the number looks similar, but there's a definitely difference here, and this is going to be R2. Okay, so that was part B. We just solved this part, calculate the altitude of the satellite. Okay, and then the last part, go ahead and, the last part here is we have to calculate the orbital speed of the satellite. And actually, I just want to bring this up now. These two particular questions, after you solve the first part, where you solve for a regular or a total radius, R, when we solve for that, once we did the first part of the problem, these other parts of the question is actually interchangeable. You don't have to do it in this particular order. You actually could have calculated the orbital speed of the satellite second, and then the altitude of the satellite third. Up to you, whatever your preference is. Okay, and orbital speed, again, based on Kepler's law, orbital speed equals the square root of the gravitational constant times the mass over r. Now, you guys already have these values written down, so I'm just going to go straight into calculating the orbital speed, which I think is one of the easiest ones. So orbital speed is going to be Vt equals square root of 6.673 times 10 to the negative 11 times the mass of the planet, which is, again, 4.78 times 10 to the 24. And actually, here's a neat trick, because writing that down should seem familiar to you because you already did it. Okay. If you look at this part from earlier, let me highlight it right here. If you look at this part, we actually did that in part A. So if you refer back to that, if you want to take a brief shortcut, you already multiplied those two numbers together, and that could save you some extra time as well. But let me finish the rest of this. Total R was 508 million 019.4 meters. Okay, and let's keep going. VT, okay. Whether you multiply it or just refer to the part A of the problem, it comes out to 2.78 times 10 to 14. All right, and you're not restricted to 2 decimals. You can round as far as you feel comfortable. And this is divided by R. .4, and then you go ahead and divide those two values in the square root sign. Okay, that's a must. And just remember, if you don't put it in the calculator under parentheses, it's not going to put out the number that you actually want. Okay, it actually does this sort of its own order of operations. And when we do this, when we divide the two numbers, we get 546,000 point. Oops, sorry, not point. 546,798.45. And your last step is just going to be to square root both sides here. And when we do that, we're going to find out that the orbital speed of the satellite here is 739.45 meters per second. Okay? And that is the final answer for part C. Okay? If you got a round there, it's quite acceptable. It kind of varies based on how much we rounded here, or how much you decided to round. So for those of you who more or less took the whole number, you are going to get a different answer, but it's not going to be too drastic. So we may be about 10, 5 off, depending on how you solve the problem. But otherwise, if it's around this answer, you solved the problem correctly. Okay.